This is the video for section 1.2.2, instantaneous velocity. Previously, we'd looked at the idea of an average velocity. So the average velocity is when we took two separate points and evaluated the position of a particle at that time, and then took the difference of times and turned that into a velocity by doing change of position over change in time. The instantaneous velocity is what we get as we turn this thing into a limit, as we let that time interval get smaller and smaller and smaller. What is happening to that average rate of change? And this gives us the instantaneous velocity. The book denotes this as IV t sub a, t is equal to a, this little notation right here. This isn't like some widely used notation, it's just what the book is using to distinguish between the instantaneous velocity at a particular time and the average velocity over a specific interval. So that's all that notation means, don't get too caught up in that. And so the idea that we have, first of all, is that we can take b as the value v approaches a and plug into this formula. However, it kind of makes sense because we're thinking of smaller and smaller time intervals to try to capture that idea of a small time interval. And so what we do is we replace the b with a plus h, and this value h is going to represent a really small number. So we're looking at the time, the average velocity between the time a and a plus a little bit, and then we're going to let the h go to 0. And that's what this second formula down here is. It's just another way of writing the same thing, but in a way that sort of draws on our intuition of what we're actually trying to accomplish. We're looking at really small time steps, and so we can say h goes to 0 and capture that idea of small times h. So for this section, there are two activities. You should take the time to go through these activities on your own first, because the practice of thinking through it on your own will help you understand things a lot better than just watching the video happen. So if you haven't taken the time to do the activity, take about 5 minutes. This is not a long activity. So take about 5 minutes and see what you can do. And if you get stuck, it's okay. I'm going to go through the whole thing in this video, but it's really worth making the effort to try it on your own first. Okay, so what do we have? We have a moving object, and the position is given by s of t equals t squared, where s is measured in meters and t is measured in minutes. So again, these units here, meters and minutes, they just help us when we try to turn this thing into a picture that we can understand. Determine the most simplified expression for the average velocity of the object on the interval 3 plus h, where h is some positive value. All right, so in order to do this, we have to remember the formula for the average velocity. So average velocity on the interval 3 to 3 plus h is equal to s of 3 plus h minus s of 3 over 3 plus h minus 3. So the position evaluated at the endpoint minus the position evaluated at the starting point divided by endpoint minus starting point. Remember that this is a slope, so this is like y2 minus y1 over x2 minus, x2 minus x1, and you just plug it in. So here we go. 3 plus h squared, because our function is t squared, minus 3 squared, which is 9, over, well, let's just simplify this. 3 plus h minus 3, 3's cancel out, you're left with an h. Let's move this below. 3 plus h squared, 9 plus 6h plus h squared minus 9 over h. These 9's cancel out. You have 6h plus h squared over h. You can factor out an h from the top, and they'll cancel out the h on the bottom. I'll go ahead and write out the factorization step. 6 plus h over h. Then those cancel out, leaving you with a 6 plus h. And so that is the most simplified expression for this average velocity. Now, in order for us to do part B is asking us for a specific average velocity, 3 to 3.2. So the question is, what value of h is needed to get the point 3.2 in our second position? And that says h is equal to 0.2, because 3 plus 0.2 is 3.2. So you can plug it in, and we get the average velocity from 3 to 3.2 is, well, 6 plus h, 6 plus 0.2, which is 6.2. Part C asks you to determine the instantaneous velocity when t is equal to 3, and to include answers. Oops, forgot the units. So in the units here, we have our s is measured in meters and t is measured in minutes. So this is meters per minute. Okay, determine the instantaneous velocity. So what is instantaneous velocity? The instantaneous velocity at t is equal to, what was it, t is equal to 3, is equal to the limit as h goes to 0 of the average velocity from 3 to 3 plus h, which we have already calculated. This is the limit as h goes to 0 of 6 plus h. Now in this case you can plug in h equals 0. There's no division by 0, there's no square roots or negatives, and you just get 6, and of course units, meters per minute. All right, so this exercise is really just the algebra up front, and then thinking through the meaning of h. Remember, h is the step size, the size of the time gap from when we start to when we end, and so in this case we pick it to be a particular value. And then instantaneous velocity is what happens when you take the limit as h goes to 0. Activity 1.2.4 has the same idea, except now we have to do it looking at a graph. Again, please take a couple minutes to try to do this yourself before just jumping into the video. There's really a whole lot you can learn from thinking through it on your own, and just watching me do it is just not the same. Okay, so here's the graph of the position S of our object, and we are asked to use the graph to estimate the average velocity of the object on each of the following intervals, from 0.5 to 1, 1.5 to 2.5, and 0 to 5. So what does that mean? We need to look at the position of the object at these different times, so 0.5 and 1. So at t equals 0.5, we're here, t equals 1 is here, and you see that in both of these points, it's about equal to 1. So if we wanted to calculate the average velocity from 0.5 to 1, we're going to have the position at 1, s of 1. I'm going to write this out one more time, minus s of 0.5 over 1 minus 0.5. I'm not going to keep writing this one out because hopefully you'll be able to get used to it and just sort of think through with me. This is equal to, so when we evaluate at 1, we get 1. So we get 1 minus 1 over 1 minus 0.5 is 0. You get the average velocity of 0. From 1.5 to 2.5, average velocity from 1.5 to 2.5. Let's go ahead and erase these points. Let's take a look. So 1.5 is here. 2.5 is there. And so if we look at the value, the average velocity is going to be the endpoint, which is going to be height 3 minus 1 over 2.5 minus 1.5, which is going to be 2, because 2 on top, 1 on bottom, 2 over 1 is just 2. And so that's that value. What about from 0 to 5? So 0 is down here, 5 is right here. Looks like 5, 5. So the average velocity from 0 to 5 is equal to 5 minus 0 over, so this is the height 5 minus height 0 over the end time 5 minus 0, which is going to be 5 over 5, which is 1. Draw each line whose slope represents the average velocity that you seek. So the average velocity that we seek and the line that connects them, I should have done this all at once, but too late now. Let's stick with black. We had these 2 points, and the line for those 2 points is just that one. And let me change different colors. Let's use red for the next one. So between 1.5 and 2.5, so 1.5 is here, 2.5 is here, and we get a line that looks like that. And if we use 0 and 5, we get a line that looks like that. All right. So these lines that connect these 2 points, they're not really that exciting right now. They do provide us some intuition with what's about to happen later, which we'll get to when we get to it. But the idea is that we're looking at the slope of these lines that connect these 2 points. This whole difference quotient right here is a slope calculation, y2 minus y1 over x2 minus x1. And so it's no surprise that the slopes of these lines correspond to these values over here. Part B, how can you use average velocities or slopes of lines to estimate the instantaneous velocity of an object at a fixed time? So the idea, let's simplify some of this picture here. Let's just pick 2 arbitrary points this time. Take this point here and this point here. So the idea of using average velocities, so let's say we want the average velocity at 2. The idea is that we want to think about what's happening to the slope of this line as this point gets closer and closer and closer to the x equals, or in this case, t equals 2 value. And what you'll see, hopefully, is that as you draw this line in closer and closer and closer, you're getting something that approaches the tangent line right here. And so that's the concept. That's the idea. Use the graph to estimate the instantaneous velocity of the object when t is equal to 2. So what we're going to do is we're going to take this t equals 2 point. We're going to take this t equals 2 point. And what we're going to do is we're going to do our best to sketch the tangent line. Now this is always going to be a little bit sloppy, and especially because I'm doing this on a computer, it's even sloppier, but you know, on a physical sheet of paper you can take a ruler and try to really line things up. But close enough. That's not bad. All right, so we have something that's basically a straight line here, and if you sort of look at the rise and the run, let's do this sort of thing. Right, so the rise is 2, the run is 1. That looks like a slope of about 2, and so that's the estimate. Should this instantaneous velocity at t equals 2 be greater than or less than the average velocity of 1.5 to 2.5 that you computed in A? Why should that be the case? Well, in this case, it's actually hard for us to know what's going to happen. Let me get rid of my sketch here, because we actually got that the sketch that I drew and the values that we used up here gave us the same value. Slope is about equal to 2. In general, what you can do is you can take a close look at this. And just think about what's happening on the graph. This is a little bit difficult. Let me get a zoomed in picture on that. Okay, here's a very, very zoomed in picture of it. And what you can see is you can sort of see that there's a slight bending here. It's not exactly a straight line. It's kind of got a slight bend if you connect from here to here. And so you expect the actual slope to be just a little bit steeper here than the average slope here to here. Now, this is a very, very graphically oriented calculation that we're doing in our heads here. I'm going to exaggerate it a little bit to sort of show you what's going on. So we have the endpoint here and an endpoint here. And you can see that right here, it's got a slight leftward bend to it. I'm going to exaggerate that like this. Right, and so you can see that if we connect these two lines right here, or sorry, connect these 2 points right here and here, you can see that the slope right here is steeper. Basically, because it started slow, with not quite being steep enough, it has to get steeper to get caught up. Don't worry too much about this particular question. This is actually related to some very nuanced ideas that we'll run into a little bit later. For right now, just sort of go with your intuition and think about this picture and just imagine connecting those 2 points and then thinking about the idea of this starting slope, because it has to make this slight leftward bend before it bends to the right again, is going a little bit too slow, and so it has to speed up to get caught up, and that's why the slope right here in the middle is bigger than the slope that's connecting these two. But again, this is a very nuanced, subtle picture. Don't worry too much about it. Just try to ride the intuition of thinking about the slopes.